we ask, how can we know something about outer space, something 10 billion light years away? The answer is to ask the question, how do we know what we see in front of us? If we strike a match and look at the flame, what is really happening is something is going from the flame into our eye and causing a nerve to trigger, giving us a sensation. In our brain, connect these sensations to make a picture. It's the same thing for outer space. Something travels from out there into here, whether the receiver is our eye or some technical device in a telescope. We need to be clear and have our understanding based in operational definitions. How do we know what we have? Like, how do you know you have oxygen? It's a clear glass that when you stick a glowing piece of wood into it, it bursts into flame. No other gas will do that. So you operationally know how to see, is this oxygen, and what you mean by oxygen. Well, we start off in the academic world, especially in theoretical physics, with many abstract terms and confusions. One of the basic confusions has to do with light, calling it a wave in some circumstances, calling it a particle in others, calling it a wavicle in others, with various kinds of mathematics for different descriptions of different investigations. These things are relatively easy understood if taken a step at a time. There's nothing magic here. It's not a probability. It's a reality, and we can look into it. And we'll see that electromagnetic radiation is physical objects moving in space like a fish swimming in water. To back up and deal with time, time is dependent on other things. It is not basic. What do I mean by this? It takes motion to have time. So motion is more important. And to have motion, you need to have matter and space. So matter and space and motion are more fundamental than time. If you have matter and motion and space, you can operationally define time. We operationally define a clock by an object in constant motion, whether it's going in a circle or in a straight line. What distance it travels and how fast it's going is how we operationally define time. That's often confused. Biologically, you can slow down time by cooling something down. At absolute zero, there's no motion, even on the molecular level. That just put something in the freezer and bring it down, or whenever you can slow down the biological clock to essentially turn it off. That's why they talk about suspended animation. The problem with that is you have to freeze so fast that ice crystals don't form. If you in normal freezing on a larger body, it can't get the heat out fast enough, and ice crystals form and they pierce through the cell membranes, killing cells in the process of freezing. So that's why you talk about quick freezing, and you can only quick freeze and bring back to life things of a smaller body shape. When we freeze meat, the reason when we thaw it out that the flavor changes, we need to cook it as soon as it's thawed out, because in the process of freezing, ice crystals grew and broke through the cell membranes, spreading the inner chemistry with the surrounding chemistry. While it's frozen, that's not joined and doesn't have that negative effect. But if you thaw it out and then save it and freeze it again, it changes flavor because the chemistry from inside the cell and outside the cell are mixed. Time is not fundamental. Time is if you have an object moving at a constant speed. We say that speed, once we have a clock, we define time by the clock. That the speed is the distance traveled by the time it took. Like the car going 50 miles an hour. In 1 hour it would travel 50 miles. But in fact, we back up, there was something moving at a constant speed to bring out the hours. And there had to be motion involved for there to be any speed, and there had to be motion involved for there to be any time. And there had to be matter, and there had to be space. Now we can talk about mathematical abstractions and in Never Never Land make all kinds of imaginary things, but life is too short. Let's stick with reality. So time depends on motion and matter and space. Now, leaving that behind, the next is about the redshift. Redshift has to do with light. Like there's a certain spectrum of light from hydrogen, but there's an effect if that hydrogen emitter is moving towards you, it bunches the waves up, and that's called the blue shift. If it's moving away from you, the waves getting to you, the period in between pulses hitting your detector is longer. That's called the redshift. All that we observe from outer space, except for some high energy particles like from the sun, some cosmic particles, which are from a relatively close distance compared to what we see with radiation, with electromagnetic radiation in terms of light years away. That whole spectrum of radiation travels at the speed of light. It's the same physical reality operational for these objects called photons. On one end we have radio waves given off by wires with a magnetic field moving back and forth, and we'll get into the reality of that later on. And then molecules oscillating, giving off microwaves, and then the outer or the lower energy electrons in an atom changing energy level, giving off light. The inner electrons giving off energy we call X-ray. In the nucleus, high energy radiation we call gamma radiation. All of this whole spectrum travels at the speed of light. And as I say, we'll get into that. But the first video will be on the redshift or Doppler effect. Redshift means it's going away, blue shift it's coming towards you. Whether it's the gamma radiation or radio waves, if you know what the frequency, what the wavelength, the distance between waves should be, if it's moving towards you, they appear closer together. You can tell from that how fast it must be moving towards you or away. And there's a hypothesis about this called the redshift that can get into Never Never Land, and they do in the academic world. And they have a magic creation story. But that's another story. For now, we're going to be looking into what we observe from the universe. This is observations. Thank you.